common rule of thumb for estimating the carrying capacity of aluminum is 9,000 pounds per square inch, often abbreviated as SI. This means that a 1-inch thick aluminum plate theoretically can support a load of 9,000 pounds. This figure serves as a quick estimation tool, providing a general idea of aluminum's strength under load. However, it's crucial to understand the limitations of this rule of thumb and the factors that influence the actual carrying capacity of aluminum in real-world applications. Firstly, the specific alloy of aluminum significantly impacts its strength. Aluminum isn't typically used in its pure form for structural applications. Instead, it's alloyed with other elements like magnesium, silicon, copper, and zinc to enhance its mechanical properties. Different alloying elements and their proportions result in a wide range of aluminum alloys, each possessing unique strength characteristics. For instance, 6061 aluminum alloy, commonly used in aerospace and automotive applications, has different strength properties compared to 7075 aluminum alloy, which is known for its high strength and is often used in aircraft structures. The 9,000 SI rule of thumb may be reasonably accurate for some alloys, but it can be significantly off for others. Therefore, it's essential to consult material data sheets and engineering specifications for the specific aluminum alloy being used to determine its actual yield strength and tensile strength. Secondly, the temper of the aluminum alloy plays a crucial role. Temper refers to the heat treatment and processing methods applied to the aluminum alloy to achieve specific mechanical properties. Different tempers, such as 6, T4, and O, result in variations in strength, ductility, and hardness. For example, a 6061 aluminum alloy in the 6 temper is significantly stronger than the same alloy in the annealed or O temper. The heat treatment process involves controlled heating and cooling cycles that alter the microstructure of the aluminum, affecting its strength. The 9,000 SI rule of thumb doesn't account for the temper of the aluminum alloy, so it's important to consider this factor when estimating carrying capacity. Material data sheets specify the mechanical properties of aluminum alloys for different tempers. Thirdly, the thickness of the aluminum material is a critical factor. The 9,000 SI rule of thumb assumes a 1-inch thick plate. However, the carrying capacity of aluminum is directly proportional to its cross-sectional area. A thinner plate will have a lower carrying capacity, while a thicker plate will have a higher carrying capacity. For example, a 0.5-inch thick aluminum plate will have approximately half the carrying capacity of a 1-inch thick plate, assuming the same alloy and temper. Fourthly, the mode of loading is important. The 9,000 SI rule of thumb generally applies to tensile loading, where the aluminum is being pulled in tension. However, aluminum structures are often subjected to other types of loading, such as compression, bending, and shear. The carrying capacity of aluminum can vary significantly depending on the mode of loading. For example, the compressive strength of aluminum may be different from its tensile strength. When subjected to bending, the aluminum experiences both tensile and compressive stresses, and the carrying capacity depends on the section modulus of the structural element. In shear, the aluminum is subjected to tangential forces, and the shear strength determines the carrying capacity. Fifthly, the geometry of the structure influences the carrying capacity. The shape and configuration of the aluminum structure affect how loads are distributed and resisted. For example, a hollow aluminum tube will have a different carrying capacity compared to a solid aluminum bar of the same cross-sectional area due to differences in the section modulus and resistance to buckling. Structural elements with complex geometries, such as those found in aircraft wings or automotive chassis, require detailed stress analysis to determine their carrying capacity accurately. Sixthly, the presence of stress concentrations can significantly reduce the carrying capacity of aluminum. Stress concentrations occur at sharp corners, holes, and other geometric discontinuities in the structure. These features can amplify the stress levels in the material, leading to premature failure. The 9,000 SI rule of thumb doesn't account for stress concentrations, so it's important to consider these effects in structural design. Stress concentration factors can be determined using finite element analysis or experimental stress measurements. Seventhly, the presence of defects can impact the carrying capacity. Material defects, such as cracks, voids, and inclusions, can weaken the aluminum and reduce its ability to withstand loads. These defects can arise during manufacturing processes, such as casting, welding, or machining. The 9,000 psi rule of thumb assumes a defect-free material, so it's important to perform non-destructive testing, such as ultrasonic inspection or radiographic inspection, to detect and assess the severity of any defects. Eighthly, the temperature of the aluminum structure can affect its carrying capacity. The strength of aluminum decreases with increasing temperature. At elevated temperatures, the aluminum alloy may experience creep, which is a time-dependent deformation under constant load. The 9,000 psi rule of thumb is generally applicable at room temperature. However, at higher temperatures, the carrying capacity may be significantly reduced. Engineering handbooks provide data on the temperature dependence of aluminum alloy properties. Ninthly, the effects of corrosion need to be considered. Aluminum is susceptible to corrosion, especially in harsh environments. Corrosion can weaken the aluminum and reduce its carrying capacity. The 9,000 psi rule of thumb doesn't account for corrosion effects. Corrosion protection measures such as anodizing or painting can be used to mitigate corrosion and maintain the structural integrity of the aluminum. Tenthly, fatigue loading can lead to failure. Aluminum structures subjected to repeated loading and unloading can experience fatigue failure, even at stress levels below the yield strength of the material. Fatigue failure occurs due to the initiation and propagation of cracks. The 9,000 psi rule of thumb doesn't account for fatigue effects. Fatigue analysis is required to determine the fatigue life of aluminum structures under cyclic loading. In summary, while the 9,000 psi rule of thumb provides a convenient starting point for estimating the carrying capacity of aluminum, it's essential to consider the factors that can significantly influence the actual load-bearing capabilities. These factors include the specific alloy, temper, thickness, mode of loading, geometry, stress concentrations, defects, temperature, corrosion, and fatigue loading. Consulting material data sheets, performing detailed stress analysis, and conducting experimental testing are crucial steps in ensuring the structural integrity and safety of aluminum structures. It's also important to note that safety factors are typically applied in structural design to account for uncertainties in material properties, loading conditions, and manufacturing processes. The safety factor is a multiplier that is applied to the calculated load to ensure that the structure can withstand unexpected overloads or variations in material strength. The appropriate safety factor depends on the application and the level of risk associated with failure. For example, aircraft structures typically have higher safety factors than building structures due to the potential consequences of failure. In conclusion, the 9,000 psi rule of thumb serves as a valuable tool for quick estimations, but it should not be used as a substitute for thorough engineering analysis and design practices. Understanding the factors that influence the carrying capacity of aluminum is essential for creating safe and reliable structures.